All right. Happy Thursday, week 2. We made it this far. We are in chapter 4. Um, Tonight will be a shorter class period, class meeting. I already said this off camera, but I want to make sure those of you on camera can, or that are listening, watching the video later can hear it. It'll probably be maybe 45 minutes, an hour max. If there's a lot of questions, it won't be that long. And I love chapter 4. Chapter 4 is super useful. I use it all the time in day-to-day things. Well, my day-to-day things are mostly just me being curious about data sets, saying, I wonder what would happen if, or I wonder what this means, or you know, analyze things. I do things like that a lot. I do math for fun. We also will be looking at lab 3 at the end of at the end, and lab 3 is pretty, it's not too difficult. I know I said that about lab 2, but I didn't think lab 2 was too hard either. Once you get to know Excel and start using it, it's really not that bad. So we will be doing lab 3 at the end. Uh-oh, I didn't even open it on my computer. So, well, I will deal with that and when I deal with that. All right. So, chapter 4, we're going to be looking at scatter plots, and then we're going to be talking about the linear correlation coefficient. Don't worry if you don't know what that is. I will tell you what that is. And we're going to talk about whether or not there's a linear relationship between two variables. So, whether or not two things are correlated. And then, real quickly, we'll talk about correlation versus causation. And I'll probably pop over to one of my favorite sites that pretty much proves that correlation doesn't equal causation. And we will find the least squared regression line, and we will do a little bit of analyzing what we can do with that. Then at the end, as I said, we're going to do lab 3. And then we'll have a little bit of a break before we get to lab 4. We're not doing lab 4 next week. It'll probably be the week after. And next week is our test. Don't forget that. You should have an email in your inbox if you haven't already checked it for the practice test. It is there. You'll need to download the lockdown browser and use the Respondus program to access it. And it's just non-curricular questions. So it's things like, what's 2 plus 2? It's super simple. It's basically just testing the software. That's all we're doing is testing the lockdown browser, making sure you can get in and all of that. And you will get a few extra credit points for that. I'm not a big extra credit person. I believe you should just do the regular credit, but sometimes in order to get people to do things, extra credit is good. So um, that kind of highlights how important it is that you do that practice test. So without further ado, uh-oh, somebody's calling me. I am not answering it. It is that potential spam person. Let me, I had to mute my watch. All right. Okay, so a little bit of vocabulary here. So response variable. So a response variable, it's another term for dependent variable. Usually this is the one that's on the y-axis, so this would be your y value. The response variable happens because something else happens. So for example, miles per hour. Hours, um, if hours don't pass, you don't go any miles. So how many miles you travel is in response to how much time passed, if that makes sense. And so the explanatory or predictor variable will be your independent variable. It's the thing that's going to happen whether or not the other one happens. Time is going to pass whether or not you are moving in the forward direction, whether or not you're traveling. Time will continue to pass. So in the miles per hour, hours the hours dictate how many miles you travel. So since the hours are in charge, that is the explanatory or the predictor variable. So whichever one drives the bus, that one is your explanatory variable. It is not always super clear. Sometimes there are things, one of them doesn't cause the other one to happen. So then it doesn't matter which is which. You just need to choose. So sometimes there's not one that's causing the other to happen. So scatter diagram. The scatter diagram, same thing as a scatter plot. It shows the relationship between two variables. And you're going to be creating one of those in Excel, and I'll show you how to do that at the end of class. And so every individual in the data set. Each, like you'd ask one person two questions or one car traveling miles per hour. So, or ask one person, how much coffee do you drink every day? How many hours do you work every day? So it's one data value or one data point on the scatter plot that represents both of those things, the amount of coffee they drink and how many hours they work. That's just the variable that popped into my head, variables. Okay. So I'm going to show you the scatter plot with this data right here. I forgot I wanted to pull this up. Nope, it's going to be on the next screen. I'm going to show you a scatter plot with this data right here. So we're going to use this data a couple of times in this class. So this shows how long it takes to drill 5 feet based on the depth at which you begin drilling. So the thing that's driving the bus is how deep you start drilling. And then that's going to determine how much time it takes to drill 5 feet. You're not drilling 5 feet unless you start drilling. That's kind of how you determine which one's explanatory and which one is the, which one is it? Explanatory and which is the response. I couldn't think of the word. So this one right here would be your explanatory. And then this one is your response. All right, so I'm gonna show you what that scatter diagram is gonna look like. So all I did was put on the horizontal axis, I put depth, and on the vertical axis, I put time. And then I just plotted each of the points. So it's just plotting it on a coordinate grid. You can't see the grids here, the squares, but all I did was just plot it on the coordinate grid. And so you can see that as we start drilling at a deeper depth, in general, it's going to take us longer to drill 5 feet. You can see that in general, if I was going to draw a line to represent it, it would look something like this. There we go. It would look something like that. And that's basically half it through the middle of our data. It's a little bit off, but it is basically through the middle of my data. I would draw that line and I could kind of use that line to make some predictions. That's what we're going to be doing today. Okay. So here's an example. There's a golf pro. He wants to investigate whether the relationship between the club head speed, so how fast he swings the golf club, and how far the ball travels. I mean, it doesn't take a rocket scientist to think to determine that it's going to go farther if the golf club is going faster. Duh. So he wants to make sure that he is eliminating as much bias and problems as possible. So like if I had different people swinging the clubs, different things would happen. If I had different club types, different things would happen, different ball types, weather conditions. So what he does is in order to eliminate that variability, he's using the same club on all of them, the same ball type of ball, a single golfer, and it's a 70-degree day with no wind. So perfect conditions out there. And they're recording the speed of the club head, and then they measure the distance that the ball travels. And so on the next slide, I have some data. It's right here. It's this lovely data right here. Is there? No, I don't know why my graph didn't show up. That is really strange that my graph didn't show up. I'm going to pull it up on my other screen. I don't know. That is really strange. I'm going to pull it up on my other screen so I can just try to like replicate it as best I can. Sometimes things just disappear and then we just roll with it. That is the wrong thing. So we're on Thursday, week 2. Uh, yeah, see, I knew that today was a day of technical issues. It's okay. All right. I think it just like when I printed it out, it just decided to get too pale. So I'm just going to draw. Uh-oh, that's weird. Okay, let's just draw a line here and then draw a line here. This software does this nice thing where it snaps to it. So we're going to start at 98. 99, 100, 101, 2. I'm not gonna, I think in your homework you might have to plot the points by hand, or they like have you put the dots on there. I can't remember. And then starting from here, we have 240, and then we're going up by fives, 245, 250. So we're just going to be doing the best we can. 255, 260, 265, 270. We're going all the way up to 280, 275, and then 280. Okay, I'm just going to do the best I can because that's all I can do. Okay, so at 100 miles per hour club head speed, we go about 257. So that would be about right here. And then 102, I'm just going to plot each of these points. Hopefully in your printout, you have the nice grid. 103, we're at 274. See, the thing is, there could be some error there because it's not going to be exact. It could be error, like there could have been rolling. They could have hit it not exactly center. There's so many different things that could have happened to cause this to not be super linear. Okay, 100, 263, 99, got 258. There's a lot of different factors that could be considered here. Okay. All right. So this is the best I'm going to do without my grid there. It's not too terrible. It could have been much worse. All right. So as you can see, as the club head speed is faster, my ball is going further. If I was to draw a line through it, it would going through the middle of them, it would look something like this. If I was going to draw a line through it, that would be a line that kind of fits the data the best. And it would be as close as I can get to a nice line if I was going to be making predictions. So if I wanted to make a prediction of how far I think it would go, if my club head speed was 104 miles per hour, I can look at it and say, okay, it looks like maybe about 273. It's just a guess, but made with what I have right here, that's the best guess that I can do. We're going to get a little bit better as we move on through this lesson, but just with what we know right now, with what I can see right now, 273 is about as good as I'm going to get. All right, any questions on this before I move on? All right. Okay, so we have some different types of relations in our scatter diagram. I'm going to make this a little bit smaller so y'all can see it. So what we are looking at here is we are focusing in this class on linear relations. We are not focusing on any of the nonlinear relations. If you go on to Math 244, you might, or Stats 244, you might move into some of the nonlinear relations, but we are focusing solely on linear relations. So if I say that there's no linear relation, it doesn't mean there's not a relation at all. It just means it's not linear. So if you take a look at this first one here, we have a nice linear relation. If I could draw a line through it right there, and it lines up pretty good with that line. And this is a positive linear relation. Because it has a positive slope, reading it from left to right, it is going uphill. So it has a positive linear relation. The one on the right, the second one, this one also is linear, but it is a negative linear relation. I can draw a nice line through that. And this is a negative linear relation because the slope of it, though it is kind of going in a linear pattern, that slope is definitely negative. This is an A. This is not an E. It just looks like one. So that is a negative linear relation, but it is definitely linear. So down on the bottom left, this is definitely not linear. If you took math 65, you might recognize it as a parabola. It is a it's negative, so it's upside down, would have a negative leading coefficient. Don't worry if you don't know any of that or don't remember any of that, not a big deal. But this is parabolic, but it's not linear. I mean, I can draw a nice pretty parabola through that, but it is not linear. And then this next one right here, if you were in Math 95, you might recognize that it is cubic. I'm not going to make you remember that, but just because I'm a math nerd and I can see that it's cubic, but it is definitely not linear. And then the last one is just super scattered. And yeah, you're probably saying, I can draw a nice line this way through it. But I mean, I guess technically that would be true, but it's not supposed to look like that. It's supposed to look super scattered. There's no relation of any kind, linear or nonlinear. It is just completely scattered and wild. And I'm not going to give you anything I mean, you may have to say that there's no relation, but it's not going to look quite as linear as this. It would have things like, let's have some dots over here and over here. See this one right here, you can kind of more see it's not linear when I add those extra dots there, or that there's no relation. Let's take this a step further onto the next page. So a positive association, I already kind of mentioned that. If it is has a positive slope and it looks linear, then it has a positive linear relation. So as my independent variable increases, so does my dependent variable. So they both go up, they both get bigger. That is a positive relation, positive association. Negative association, if it's sloped downward, so if one of my variables is getting bigger while the other one is getting smaller, then it has a negative association. So as you're going from left to right, if it's going downhill, that's a negative association. I'll give you a moment to write things down if you need to, since I know some of you don't print. I'll give you a moment. If basically if you said positive slope and negative slope, it's going to be helpful. Make sure you holler at me if I move too fast, please, please. Sometimes I do. I get excited because I like the math. And see, since I'm not teaching the high school right now because it's summer, you all are all I get for my math fix. You're it. Okay. Don't worry about this equation. It is big and ugly and scary. Don't worry about it. This a linear correlation coefficient. So what this number does is this number measures the strength and the direction of the linear relation between two quantitative variables. So it's going to tell you how strong our linear relation is, how strong it is, how correlated the two values are, the two variables, and it'll tell you whether it is positive or negative slope. That's what the correlation coefficient does. We frequently just call it an R value. I'm going to write that down because we call it that all the time. So we just call it an R value. So if your R value is super close to 1 or -1, it would be a very strong linear relation. Don't worry, I'm going to get a little bit more detailed in a minute. It's a very strong linear relation. If my R value is close to 0, then there's either no linear relation or a very weak one. This is the equation, this is the formula to calculate the linear correlation coefficient, but I will never, ever, ever make you do it by hand. And I highly recommend not trying it. It is very, very tedious because basically what's going on here, I'm just going to show you. You find the z-score of every single x value. You find the z-score of every single x value. And you find the z-score of every single y value. So I take the x value z-score, multiply it by the y value z-score. That's one individual's answers. Then I take the next x value z-score, multiply it by the y value z-score. I do this with each of the data sets, data values, and then I add them all together. And then you divide them by n-1. It is super tedious. I'm never going to make you do this in real life. Just letting you know, it's very tedious. Don't do it.
So should we not write this down?
Do
This
not write
form.
this down.
Okay. Okay.
I mean, and if you decide, hey, I really want that, you can come back to the PowerPoint. You can go to your textbook. You can Google it.
Looks
Don't.
like a mess. I'm good.
I've done them by hand several times, and no, just don't. I actually have fancy ways I do it in my calculator, but I'm not even going to teach you that. Like the fancy ways to like hand calculate it to make it quicker. I'm going to just give you a function that is just going to pull that right up, and you don't have to do any math at all. The only math you have to do is putting it in your lists in your calculator, and you all know how to do that already. All right.
Yeah.
Yep, we did that last class. We put those in the L1. So we're going to do L1 and L2, but same thing. All right. So here's some things, you don't have to write all these down, but here's some things to know about our correlation coefficient. It's always between -1 and 1. If somehow you did something to get a value greater than 1 or less than -1, you did something wrong. So it's between -1 and 1, always. If R is exactly 1, then it's a perfect positive linear relation. If it is exactly -1, it's a perfect negative linear relation. If it's really close to 1 or really close to -1, then it's a strong linear relation, either positive or negative. If it is close to 0, I see I already said this once, but it's all written down now. If it's close to 0, there's little or no evidence that there's a linear relation. So it's closer to 0 means that there's no linear relation or super weak. Um, we don't we don't attach any units. The R value is just a value. So there's no units for it. We just say that the R value is 0.93, and then we can interpret it. It's not resistant. Therefore, if you have an outlier, it's going to pull your R value into the outlier's direction. So outliers will drag your correlation coefficient. So just be aware of that. Okay. So here are some examples of what different correlation coefficients look like. So letter A is a perfect positive linear relation. And B is strong positive. It's about 0.9. So A is our value is 1, and B, it's about 0.9. Now, letter C, this says it's 0.4, but I'm going to say that this R is more likely about 0.6. It looks much stronger to me than 0.4, and I would still call it moderate. When I get down to 0.4, I generally call it moderately weak. And I'm going to give you my rule of thumb, but the thing is, as I said, statisticians do not deal in absolutes. So depending on what you're studying, a 0.9 could consider that strong positive, or if it's something that needs to be super concise, you might consider it weak. So it really depends on you, but I'm going to kind of give you my rule of thumb, and if you kind of stick around there, you're going to get your full credit. Okay, so letter D is a perfect negative, so my R value is -1, and E, it's a strong negative, so it's about -0.9, and F is a moderate negative, about -0.4. I think it's more likely -0 point, probably 0.55 would be my guess. And then G is really close to 0. It's just that's really super scattered. And D is a nice parabola, but it is not linear. So there's no linear relation. So G and H, both of those have no linear relation. So I'm going to give you, I don't have, is there a way for me to just get to another screen? No. Okay, I'm just going to write what I do. Let me see if I have a good, don't use, I'm using this spot for something different. Ignore what's there right now. So generally for me, if I have anything between about 0.85 to 1, I call that strong. And you can say extremely strong, you can say, um, you know, moderately strong, you could say whatever adverbs you want to throw on those. I would consider anything from 0.85 to 1 pretty strong. Anything from about 0.75 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.75 to 0.85, I would call it moderately strong. 0.75 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it moderately strong. 0.85 to 0.85, I would call it Well, maybe about, yeah. So if anything from about zero point 0.6 to 0.74, I would call that just moderate. So maybe not even moderate. Let me see. Yeah, I would say that moderately linear, linear. I mean, that's what words were used back here? Moderate positive, yeah, moderately linear. And probably zero point 0.4 to about 0.59. We can call that moderately weak. About zero point 0.3 to 0.39, I would probably call that weak. Maybe 0.25. See, as I said, we don't deal in absolutes. Less than 0.25, call that it's very weak or no linear. And this goes for negatives also. So these are not hard and fast rules. These are not, this isn't like, hey, I'm at 0.59. I'm calling it moderately weak. I'm going to give you some leeway, but if you call zero point 0.4 strong, I will mark you down for it. Or if you call 0.85 weak, I'm probably going to mark you down for it. So there's a little leeway here, but this just kind of gives you a rule of thumb. And if you kind of stick with this, nobody's going to be mad at you. So, this is guidelines, not rules, if that makes sense. Kind of like the speed limit. No, kidding. Kidding. This is just, you know. No, I drive 199 every day during the school year. I am really careful because there are accidents on that road almost every day during the school year. So I am pretty careful. And whenever there's an accident on that road around my commute time, I have like at least 2 to 3 of my kids sending me text messages saying, Mom, are you okay? Mom, are you okay? Did you make it home safe? They're always so worried. My youngest, especially, she's always so worried that I'm going to die on that road or something. I did hit a deer. So me and my stories, I know I get off on tangents. I can't help it. So on March 13th, 2020, it was the day that they shut our schools down for COVID. And it was a Friday the 13th. It was the day they shut our schools down. I was on my way to work and I hit a deer on the way to work on March 13th, Friday, March 13th, 2020. And of course, because it's legal, I got out and I had to look for the deer because if I could have found that deer, we'd have had some meat, you know? And it's legal to do that now. If you hit a deer, you can throw it in the back of your car and you can take it home. I was going to call my sons to do it, but I went out there and I couldn't find it anywhere. I was pretty disappointed because I was going fast. I was probably going 60 when I hit that thing because it happened fast. It was at 4 o'clock in the morning. So I drove my car to work still. It was in pretty bad shape, but it was drivable and I still drove it to work. But that was also the day they shut us down. So it was just a really, really bad day. It did $12,000 of damage on my car. It was very sad. So there's my story that has nothing to do with what we're just doing, except for that speed limit is a guideline, not a rule. So I'm going to delete this. All right, now we're going to use this page. So we're going to determine the linear correlation coefficient of the drilling data. Yes, it was terrible, Bradley. You're right. I was okay though. Just the poor, I don't even know what happened to the deer, but it was a buck because I saw his antlers. Anyway, so I am going to flip to my calculator. We are doing this in the calculator. So let's flip over to my calculator and okay, before we do anything, everybody have your calculators handy? Have your calculator in your hand. Before we do anything, we are going to turn on a feature. It could already be turned on your calculator, but I want to make sure everybody has this feature turned on before we get started. So in order to get the R values, which are a correlation coefficient, there has to be a feature turned on. So hit the second button and then 0. This brings up a catalog. So second 0. We touched on this like last week a little bit because people were having problems. If you scroll, so second 0 brings up a catalog. Scroll all the way down to diagnostic on. Whoops, there it is. I went past it. So diagnostic on. So do second 0, then go down to diagnostic on. I'm gonna wait till everybody gets there. It's in alphabetical order, thankfully. Okay, once you're there, just hit enter, then enter, and it'll say done on your screen. I think everybody's will say done. It should. We all there? Okay. So even if it was already turned on, it's not going to mess it up by turning it on again. It thankfully it doesn't like cancel each other out or anything. All right. So now we're going to hit stat, which is right next to the circle thing, and we're going to go into our lists. So hit enter on the first option. We have our lists here. And remember, go up to highlight the L1 and hit clear enter. Do not hit delete. Hit clear enter. And this is now we're going to have this nice pretty. If you have something in L2, do the same thing. Hit clear enter. We want L1 and L2 to be blank because we're going to use both of them. So what I'm going to do is I'm going to put all of my X values, so all of the depth at which drilling begins into L1 and all of my time to drill in L2. Make sure the two data values that go together are lined up. So I'm just going to start putting them in. 35, enter. 50, enter, and just kind of go all the way down. Lost myself, 185, 190. Okay, got all of my X values in. I'm going to go back up and I'm going to work on my Y values. As I said before, the most common error is a typo in your data. That's where I make my errors.
Literally just found one as you said that
In mine or in yours?
in mine.
Okay, yep, it happens. That's what I do the most. I'm the typo queen. I'm going to look over mine before I do anything with it because I don't trust myself. Okay. Well, at least I ended in the right spot. So I'm just going to go up and check mine because I don't trust myself. And it happens frequently. 55.99, 75, 74. 130, 693. Yeah, okay. Man, those are so small. Okay, I need to make this bigger. There we go. That looks so much better. I'm getting blind in my old age. My grandkids asked me how old I was today. And when I told them, they told me, man, Nana, you are really old. I was like, well, thanks. I am. Thanks. That's the thing with kids. They're honest. Okay. All right. Does everybody have their data in there? Does anyone need another moment? Okay. So we're going to go to stat. So click stat again and arrow over to tests. So 2 arrows go over to, and I just lied to you. We still want calc. So arrow over to calc again. So once again, hit stat, then arrow over to calc. We are looking for option 4. This is a linear regression. Yes, exactly. No filter. They say they're completely honest. So we're going to go down to number 4. So number 4 says linreg AX plus B. So this right here, the AX plus B part might look a little familiar. So you think of Y equals MX plus B. We're just replacing the M with an A. It means exactly the same thing. That A is our slope. The B is our Y-intercept. I'm going to hit enter. My X list is L1. The Y list is L2. So if I didn't have L1 here, to get L1, you do second 1, and it'll put L1 there. And on the Y list, do second 2 to get L2 there.
What if it shows up um, back in the main screen and it says linreg AX plus B? I don't know
So
if you can see that.
you would do comma L1 comma L2 and then close your parentheses
Okay.
and then go down to calculate and hit enter.
Um,
Did that work?
Yeah, we're gonna see the calculator there. Comma L2. Sorry, I'm slow.
No, it's okay.
And then hit so comma L1, comma L2.
Close your parentheses and hit enter.
Error syntax. Ah,
Okay, so just a second here.
okay.
Because I'm wondering if you need to have another thing. So linreg AX plus B. What is your calculator?
It's
TI
a
what?
TI 84 plus.
Okay, let's see. Okay, let's see here. What does it say? Mm-mm-mm-mm. I'm sure that I can find it. Okay. Yeah, I don't care about all that. Okay, so there's no parentheses, just L1,
Oh,
L2. Don't put the Y1 there. So you see this right here? Don't,
yeah.
yeah, just put L1 comma L2, then don't put anything else after that and try it again.
I got some stuff.
Okay, good.
Thank you.
No, you're welcome. And I'm sure that there's people that are going to watch the video and that are going to be so thankful that you asked that question. Okay, so this should be what your screen looks like. Are your numbers the same as mine or super, super close? Hopefully exactly the same.
Mine are identical, yeah.
Good. That's exactly what we want. So this number right here, the R value right here, the bottom number, that's what we're looking at. This is our correlation coefficient. I'm going to write it on my screen that you can't see right now. That is not a pen.
Melissa, I have a quick
Yes.
question. I
Yes,
have the same numbers too, but does it matter if my calculator is not showing the zero? It just says 0.772 and
that's
then
fine.
so on.
That's
Okay.
absolutely fine. Yeah.
All right. Thank you.
You're welcome. Okay. So our correlation coefficient is 0.77. So you could say that this is moderately strong. So it's moderately strong. So we don't use the R squared a lot in this class, though I think that you might have one or two homework questions that ask you about R squared. We don't really use it a lot in this class. And I'm going to explain to you what it means. So this gives us an equation. So this A right here is the slope and the B is our y-intercept. So if I was writing an equation, it'd be y equals 0.116x plus 5.527, whatever. We're going to write that in a minute. But so what R squared tells us is the percent of the variability of our response variable that can be explained by our equation. So basically, it's saying that making predictions with my equation, making predictions about the response, about the drill time, would be about 60% accurate. So that's not super accurate. So if I'm making predictions, it's I basically got a 60% chance that I'm going to exactly hit it. So I'm going to be probably in the ballpark, but it's not going to be extremely accurate. It's not going to be a great predictor, but it'll be okay predictor, about a 60% chance. That's pretty much what the R squared tells us. So the R value just tells us this is a moderately strong linear relation. If I can put a line through it and they're going to follow the line pretty well. So I'm probably not going to make predictions. I'm going to flip back to my other screen. I'm probably not going to make predictions about the ball going, like if I begin drilling at 220 feet, I'm not going to make a prediction about drilling 220 feet because it's outside of my data. It is past my data. But I might try to make a prediction about drilling from at 125 feet because it's right in the middle of all my data, and I'm more likely to get an accurate answer than I would if I'm trying to make predictions that are outside of my data, if that makes sense. So the further we get away from our data, the less accurate we're going to be. Questions on this before we move on?
I have a question on this.
Okay, go
Excuse
ahead.
me. So anytime that we're looking for a linear correlation coefficient
Uh-huh.
on our calculator, do we have to hit second zero every time
No, that's
for
one time
shifting?
turning it on in this calculator. You should never have to do it again unless you decided to like reset the whole calculator. It is
Gotcha.
now programmed in there.
Awesome. Good to know.
Yeah, that was a great question. I'm
Thank you.
sure someone
Question
else was
two.
thinking. What was that?
Oh, could you remind me? A is the slope and B is what?
A is the slope and B is the y-intercept. So
Thank you.
you may remember y equals mx plus b, where m was the slope. Here they decided to use A because they don't want anybody to have any consistency in their math classes. I'm not bitter. Not at all. Just kidding, kidding. Okay. So
And
now,
so that is considered a moderate strong.
moderate, I would say moderately strong, yeah. Or yeah.
Okay.
I mean, if you just called it moderate, you'd probably be fine. I'm not going to split hairs on that. I wouldn't call it weak though. Just don't call
Okay.
it weak. As
Okay.
long, as long as you, yeah. Just throw the word moderate in there most of the time and it helps a lot.
Okay. Thank you.
You're welcome. All right. So now you with your fancy schmancy calculator, I would like you to do this one on your own. So go to Stat Edit, make sure you clear out those columns, and then do this one on your own. I'm going to do it on my handheld calculator and not on the desktop. That's how much I trust you. Whoa, what the heck do I have going on here? I have some weird stuff in my handheld calculator. I think it's because I have a beautiful, lovely little Skinnamarink grandson, Salem Isaiah, who loves to mess with my calculator. Once you get it, is anyone brave enough to tell me what they got? You can type it in chat. You can say it out loud. I don't care.
I got for the R value, right?
Yes.
The R value, I got 0.9386.
So
So
that's
0.94.
yep, that's what I got. Is that what everyone else is getting? About 0.94? Good job. Yay. Okay. So if you were to interpret this R value, if you were going to interpret it, what would you say? How strong is my linear relation?
Strong.
Yeah, I would just call it strong. I would say there's a strong linear relation. So if you look at your R squared, so I'm going to talk about it at 0.88. So this is saying that 88% of the variability in my distance in yards can be predicted by the equation that we come up with. So I think an 88% accuracy is pretty darn good. I still probably wouldn't try to predict anything that's like 120 miles per hour or anything, but you're going to be pretty confident when you predict I don't know, what number do I not have represented? 104. If I was predicting 104 speed, mile per hour club head, or maybe a 97 um, mile per hour club head, you're probably going to be pretty accurate in your answer because we have an 88%. 88% of that variability can be predicted by the equation. So that's not too bad. Questions on this before we move on?
I have a question.
Yes.
Um, Looking at the calculator, the
Uh-huh.
B is the slope, right?
No, the B is the y-intercept.
Oh, that's the y-intercept. Okay,
Right.
okay, okay, okay.
The
So the
A
A
is the
would be the
slope.
slope. Okay.
Yeah.
Okay, so like looking at this would be a positive trend, right?
Yes, because my slope,
Okay.
well, yeah, I mean, obviously I don't have that one up, but yeah, I have a slope of 3.166.
Yep.
Yeah, so that's a positive slope. And in most cases, when we do these, my y-intercept is kind of meaningless because obviously, because I have a y-intercept of negative 55. Um, if my club head is not moving, the ball is not going to travel backwards 55 yards. It doesn't happen. So a lot of times we have to restrict our domain in a way to say, this is accurate with club head speed starting at a certain value. So obviously at 0, it's meaningless. But maybe we could say, oh, starting at 80 miles per hour, we can use the equation that we come up with, if that makes sense.
Right, right.
All right. So let's move on then, unless there's more questions. Look, we're already on slide 14 out of 19. We are doing so great. Okay. So correlation versus causation. You cannot, in observational study, you can't conclude that two things are correlated, that if they're correlated, that one thing caused the other. You cannot say that in observational data. You can only do that in experiments. If you are controlling the outcome, then you can say that. But in observational studies, you can't. So, for example, there's the correlation between teenage birth rate and homicide rate since 1993 is 0.9987. However, you cannot conclude that higher teenage birth rates cause a higher homicide rate. That's observational data. There's other variables that are being considered here. See, I thought we were going to be done in 45 minutes. This is taking longer. Sorry about that. We're almost done. But I am still going to take a side note here because you guys are going to like this website. This is basically me showing you the correlation does not equal causation. So this site right here, it's called Tyler Vigen, which is Spurious Correlations. He has a whole book and everything. So he has things that he has correlated, found the correlations, and they don't make any sense. Just a second here. So, for example, the R value for this one is 0.966. So the popularity of the first name Christopher correlates with burglaries in Oklahoma. And our R value is 0.966. So obviously, naming your child Christopher does not cause burglaries to happen. Popularity of, let's see here, popularity of first world problems meme correlates with Google searches for Vihart. That's a 0.9. Do you guys know who Vihart is? She has some really great videos. They're math videos and they're really awesome. She's so entertaining. I could watch her stuff all day. Okay. Here's one. This is a 0.97. The sales of LP vinyl albums correlates with Costco's wholesale stock price. And I don't think Costco, I mean, they might sell LPs, but they're not like the main seller of LPs. Let's see here. Bachelor's degrees awarded in education correlates with the number of proofreaders in Kansas. There's a whole bunch of them, and you can even create your own. Popularity of the first name Lamont correlates with the burglary rates in US. There's a ton of them. There's some about cheese and margarine and all of that stuff. It's so fun. It is called tylervigen.com. I'm going to write it down for you because if you want to just look at it just for fun, I'll write it down. And then we will there's a spot where you can create your own. There you go. TylerVigan.com. It's spurless correlations, but it is loads of fun. Okay, I'm going to move on now. So there's things called lurking variables. So lurking variables, also confounding variables, but we're not going to get into those too much. So there's a lurking variable is a variable that is not our explanatory or our response variable, but it affects both of those things. So it affects the explanatory and it affects the response in such a way that it looks like one of the things is causing the other and it gives them that strong relationship. So for example, as air conditioning bills increase, crime rates also increase. So this isn't saying that using your air conditioner is causing the crime rates to increase. Both things increase as the air temperature increases. So therefore, yes, there is a correlation there, but they're not related in the sense that one thing causes the other. There is that lurking variable of air temperature. So be kind of careful of that, especially don't next week you guys are going to get your final project. When you're doing your final project, you might have to look for some of these lurking variables. The final project is going to be so much fun, and I'm really excited to give it to you guys next week. So excited. All right. But don't worry, it's not due until like the last week of class, but you need plenty of time to think of things. Bradley, I'm sensing some sarcasm there.
No sarcasm, maybe a
No?
little bit, maybe a little bit, but I'm actually really excited for it. So,
Okay, good, good. All right. So least squared regression line is also called a trend line. I'm going to write that word right here. We're also calling it a trend line. It's a trend line, it is a least squared regression line. It's also called the line of best fit. You saw me drawing them earlier, and it is a line that best fits our data. So the line that we're getting from our LinReg, that is called a line of best fit or linear regression line. And it gives us this line that could best predict our data. And as you see, that R squared will tell us how well it predicts it. So I'm not making you calculate one of these on your own. Use your calculator, use Excel, but it best estimates it. And so this helps us to make our predictions. It helps us to infer things and just trying to decide, you know, anyway. So if I'm making a prediction of that 104-mile-an-hour club head, I can use the line of best fit. So we're not going to, you don't have to re-put that other data into your calculator because I'm going to show you mine to get the line for this data right here. So I'm going to jump back. This is the data for the drilling. So drilling that hole. And we have that A right here is my slope. I'm going to write it on my, second here. My iPad did wonky things. So 0.012. That doesn't fit. I'm writing too big. So y equals 0.012x plus 5.53. All right. So I wrote the equation right here. And I'm not going to split hairs on this with you, but anytime an equation or something is a prediction, we put a hat on it. So I don't care if you put the hat or not, but this is a prediction. So I'm putting a hat on my y. So the y hat is that equation right there. So if I was going to make a prediction, so let's say that I wanted to determine 140 feet, how long would I expect it to take to drill 140 feet? I would just take the 140 and I would do this. And I would put that 140 in for X. That should be a point right in here. I lost my decimal. So it would, whoa, that's weird. I don't know what happened there. 0.012 times 140 plus 5.53. There we go. It would be, we would expect it to take about 7.21 seconds. This would be my prediction. And so I don't know how accurate it would be. It would be fairly accurate. At least we could have a ballpark. We'd say, okay, so it's going to take about 7.25 seconds to drill that far, or minutes. That's just minutes, not seconds. So we could expect it to take about 7.25 minutes, and it would be fairly accurate.
I have a question.
Yes.
So for the Y value, you've gone 3 decimal places, but for the, or I'm sorry, for the A value, and then the B value is only 2 decimal places. Is that,
It's not significant at all. It is just
okay,
me. Not
okay.
significant. Basically, I just went to two significant figures. You guys ever take science? Sig figs? So I just went to two significant figures, and there's really no like rhyme or reason to why I did that. Your my open math will tell you how far it wants you to round. So try not to worry about it. On your test, I'm not going to get mad at you. If I don't tell you where to round on your test, I'm not going to get mad at you if you're more or less than I expect. I just, if I don't know, I usually go two significant figures. That's just me. All right. So I would like you already have this in your held calculator. I would like you to get that least squared regression line from your handheld calculator. So it's already in there. You don't have to run the regression again. So you can go down to LinReg. Your L1 and L2 are already there. Go down to calculate, bring that up, and write down that equation. Oh, stop doing weird things. Just letting you know I'm going to three significant figures just because I don't want to round to 0.8.
Okay, so I'm confused.
Uh-huh.
So we go to calc linear regression, right?
Mhm.
And then we go to calculate, right?
Right.
It's just the same. It's oh, okay, I see.
Yes. So
Oh,
the A is your slope and the B is your y-intercept. That negative, did the negative get you? Is that where you lost it?
I was just curious. I was trying to figure out where to plug in these numbers exactly. I didn't know that
Uh-huh.
I was right with what I was doing.
Okay.
So,
So I'm not going to ask you to plug the numbers in, but if I was to try to predict how far the ball would go at 104 mph club head speed, you would just plug 104 in for X. You don't have to do that. Just telling you that's what you would do. Now, this is our last slide. So ask any questions about linear regression before we do the lab that you would like.
Did you say you're just plugging in 104 for X?
Yes, if I was going to calculate how far I thought the ball would go with at 104 miles per hour, I would plug that in for X. Yes, the 104.
Awesome. Thank you.
We generally will not, with these, we won't do backwards. I won't say, how fast is the club head if my ball went 270 yards? And it tends to not be quite as accurate when you go backwards, which is just kind of an odd thing, but it just tends to not be as accurate. So if you are trying to do it the opposite direction, run your linear regression with L2 as your X value and L1 as your Y value. So swap your X and Y and get that equation instead, if that makes sense. So if like, for example, on this one right here, if I wanted to determine how deep do I have to begin drilling if I want it to take 7 minutes, I would swap when I run my linear regression, I would swap my X and Y. So I would do L2 and L1 like this. Instead, I would swap them and I would use that equation instead. So you're going to have the same correlation coefficient because they're still correlated the same way, but you want the other equation. And it's just, and I'm not going to give you any good reasons, but it just works better. So if you decided you wanted to predict the other thing, swap the x and y and get the other equation. All righty. So I need to go into the bowels of my computer to get the lab 2, no, lab 3, sorry. I need to find it because I forgot to pull it up. Oh, I need it from Dropbox. So where is the lab 3 that I want? I bet it's this one right here. Let's hope it's this one right here. Looks like it. Yay. Okay. Yeah. All right. So we're going to talk about lab 3. So I told you previously the data set that or what I wanted you to grab. I'm going to tell you again. You need to find variables that you think are correlated. You're more than welcome to put, you can go online and you can talk about like the height of quarterbacks and number of interceptions they've thrown, something like that. So you can go to 20 quarterbacks and say, he's this tall. This is how many interceptions he threw last year. There's an example. You can just look that type of data up. Anything, any two things you think are correlated. You can, and you only need 20. You don't need to do 50 as the lab says. You only need to do 20. But this one, so this is made up data. So I took heterosexual couples that are married and I have the husband's age and the wife's age. So this is one couple. So these two things together, I think that husband and that wife, their ages are correlated. So I think there's some correlation here. So my population is like Facebook friends. And with the exception of, I think 2, I got all of the lab 1s graded. So there's feedback on there. So you should be able to go back into that lab and see the feedback. I think you might have to, I don't know if you have to open up and practice. I'm not sure exactly how you get in there. If somebody has found the feedback, wants to share how they got there, that'd be awesome. Anyway, so, because I can't see it from my end. I don't know I see it from like the back end, but I can't see what you see. Anyway, so I have my X and my Y. Obviously, one thing does not cause the other to happen. I really don't have a good one to be explanatory and a good one to be response. So the husband is going to be the explanatory and the wife's is going to be the response. It doesn't matter because one doesn't cause the other. This is just the way it ended up in mine. So the variables I'm studying is their ages in years. I don't care why you're interested, but make sure you tell me what your variable is. The units of my data are years. And talk about the letter D. Why are you sure your two variables have an association? I just want you to say, I think they are correlated because I think that men tend to marry women that are near their age. I don't know, make something up. Why do you think I think that taller quarterbacks throw fewer interceptions? I don't know. You tell me why you think the two things are correlated. Where did you get your data? How did you get your data? If you collected it yourself and you asked questions, tell me that. If you got it from a website, tell me that. Tell me how you got your data. All right. So I'm going to highlight my data, both columns. Actually, I think, do I want to do? No. I'm going to highlight my data, both columns. So I just did that. Once again, we're going to go to insert. If you go to recommended charts, it should give you a scatter plot. If it doesn't, you can see a picture right here. Looks like a scatter plot, and you can get it there as well. So it's going to give me a scatter plot. I'm going to go up here. And before you do anything fancy with it, if you don't like these little blue dots and you want to make it prettier, I'm going to make this a little bit bigger. If you want to make it prettier, if you want to do fancy things, do that before you start adding extra stuff to it. If you like other colors, whatever you want to do all of that first. Okay. We need vertical and horizontal We need those labels. All the labels have to be there. So up here, there should be some title that's relevant. I'm not going to put one in right now, but I'm going to add chart elements. I want axis titles. I want a primary horizontal, axis title, primary vertical. And this is going to be, this one, my X value is husband's age in years. I know it's this one's husband's because it's the X, it's the first column, and the second column will be my vertical axis, age in years, and then this one is wife's age in years. Yeah, except for I did something weird. Okay, there we go. Now the next thing we're going to add, so click on Add Chart Element, go down here to Trend Lines. Now I'm going to click on More Trend Line Options. So go to Trend Line and click on More Trend Line Options because we're going to need other stuff. I want my trend line to be linear. I can't make the bar on the side be bigger. For some reason, I can make this bigger, but not this. You want linear. Even if your data isn't linear, we want linear. Go down here, display the equation on the chart, and display R squared value on the chart. I want both of those things displayed on my chart. Uh-oh. I'm going to move them over, and I'm going to make them bigger because I like to be able to see them. So I'm going to go to Home, and I'm going to make my font nice and large. You can make it bold if you want. You can make it colorful if you want, whatever you want to do. So I have this nice gigantic, whatever you want to do with it, make it pretty, play with it. Okay. This is the equation that I would use for predictions. This is the R squared value. We talked about what the R squared value is, but we need an R value because we need that for here. I want to see your R value. So I'm going to put R equals right here. Then what I need to do is I need to take, because this is R squared, I need to take the square root of this. So I'm going to put equals SQRT parenthesis. I'm just going to type in 0.8616, and it's going to do that math. Took the square root of that. I'm going to make this bigger so you can see it. Okay. So my R value is 0.928. That is a pretty good R value. That is a pretty strong R value. Down here in F, I am going to reference my R value when I talk about how good the association is between my two variables. I specifically want you to mention the R value. I specifically want you to mention if your correlation is positive or negative. Now, every time you take a square root, you're going to get a positive number. So if this was a negative correlation, my slope of my line would be negative. I would need to mention down here that it's negative because this is going to be positive no matter what. Because once I take the square root, this number right here is going to be positive no matter what. So you are going to have to mention that it's negative. Because even if this slope of your trend line is negative, you need to mention it because my R value is not going to show that. Okay, so in here, just talk about, like I would say that there's a strong positive correlation between the ages of husbands and wives, according to my graph. My R value is 0.928, which is very close to 1. That's probably what I would say, something like that. So that is all I have for that. Any questions? Look at y'all. You got it. Woohoo. That's all I
What
have.
did you,
But go ahead.
I'm sorry, what did you type in to get the square root? You typed equals and then square.
Can you see it up here? Up by
There
this?
it is.
Yeah, that's what I typed in. So equals SQRT. If you type in SQ, it's gonna pop up and show you what the rest of it is. And then I just typed in the R squared value to take that square root. Any other questions? All right. That's all I have for y'all today. Actually, we're still recording. I'm going to get off the recording if anybody has any questions for non-recording. Just a second here. Let me stop it.